As a final speaker, I would like to thank all the participants for coming and participating in this rather broad title, complex geometry and symplectic geometry, and also Riemannian geometry. I think that the title is broad, mainly due to the scope of Dan Burns' research on mathematics. And also, I like to thank, I'm one of the organizers, but I'd like to thank the organizers, the main organizers. Yeah, he did main job, and also the Professor Jonghae Liu did all the necessary. I'm kind of commuting, and I missed several talks already, but I think the talks are somehow related. Today, also, yeah, as I already say something, a few words on Monday's dinner table, but okay. Happy anniversary again, and happy birthday. And also, I'm one of the graduates from Michigan, and he was in my doctoral thesis committee. I guess you're not, you didn't write a recommendation letter for me.
She writes only for good.
That's maybe the main reason. Okay, so today I'd like to talk about fake projective planes. These are special class of algebraic surfaces, which are interesting from both points of view, from algebraic geometry, algebraic surfaces, and differential topology and topology of four manifolds. This is not working. So here's the outline. I will go over the recent progress on the classification of fake projective planes, some definition and known constructions, and Professor Young's recent classification of fundamental groups of fake projective planes, and Cartwright and Steger's computation of actual computation using computer algebra of all possible fundamental groups. And the next two topics will be my results. Fake projective planes is very difficult to find. They don't have any moduli. They kind of isolated. So you cannot find a fake projective plane by deformation method. So with this classification, recent classification of Prasad and Jung and Cartwright and Steger, these results solved one aspect of classification problem for fake projective planes, namely arithmetic point of view in the classification of fundamental groups. But geometric point of view, we still don't know the defining equation of single fake projective plane. So to understand, or in search for a fake projective plane, I studied the structure of all possible quotients of a fake projective plane, and also like to give a characterization among projective surfaces, and to become a quotient of a fake projective plane. So this will be my main topic today. So here's the definition. it is well known that a compact complex smooth surface with the same Betti numbers as CP2, meaning that the first Betti number 0, second Betti number 1, and then by Poincare duality, third Betti number 0. This is always projective. I mean, algebraic surface can be embedded into certain projective space. Such a surface is called a fake projective plane if it is not isomorphic to CP2. There could be another definition. If it is not homeomorphic to CP2, or it is not homotopy type, same homotopy type to CP2, there is more information on fake projective plane. Canonical class, this is a divisor class of a metamorphic two form on X. Canonical class of a fake projective plane X is always ample. Well, as I said, it has second Betti number 1, so Picard number 1. So the canonical class could be negative ample or just ample. So negative ample case, you always get CP2. Otherwise, you get a fake projective plane. So a fake projective plane is exactly a surface of general type with PG0, and C1 square is equal to 9, and C2 is equal to 3. So you can characterize fake projective plane just a surface of general type with the same Betti number as CP2 with PG0. So rest of this just follow from the conditions by if you look at the so by this Betti number condition, it has always Euler number, Euler characteristic 3. And then Nesser inequality, Nesser equality, Nesser formula says that C1 square is equal to 9. In this case, C1 square is equal to Kx squared. And this universal cover is the unit 2 ball in C2. Hence, the fundamental group is always infinite. So CP2 is fundamental group is simply connected, so its fundamental group is trivial, and fake projective plane always has infinite fundamental group. So this actually the second fact is is a non-trivial result due to the work of Obeng and Yao, the solution to Calabi conjecture. In fact, so this is surface of general type. So the second canonical genus, so the self-tensor of two metamorphic two forms, that will be effective. So there will be holomorphic bicanonical form. So using this fact, you can get a this canonical form is represented by Keller form. So by this solution to Calabi conjecture, so it can be represented by Keller-Einstein metric. So it can be uniformized by this two ball. So it's always infinite quotient of this two ball. And then this fundamental group is always a discrete torsion-free co-compact subgroup of PU21. PU21 is the automorphism group of unit 2 ball. Such ball quotient are strongly rigid by most of rigidity theorem. So in other words, fundamental group determines the surface up to holomorphism or anti-holomorphism. So it doesn't deform. So their moduli space consists of a finite number of points. And the fundamental group has covolume 1 in PU21 by Hirzebruch proportionality principle. So here, maybe in this room, maybe there's some differential topologist. So in differential topology, there's another notion, an exotic CP2. So exotic CP2 means a simply, you could drop this symplectic, just differentiable four manifold. No. Yes, differentiable four manifold, homeomorphic 2, but not diffeomorphic to CP2. Or in symplectic category, you can think of a symplectic four manifold, diffeomorphic 2, but not homeomorphic 2, but not diffeomorphic to CP2. So the existence of such an object is not known yet. So of course, in complex category, it doesn't exist because homeomorphic means it must be isomorphic to CP2. The known constructions, David Mumford proved the existence of such a surface. So he was the first who proved the existence. And his proof is rather abstract. So even algebraic geometry point of view, so based on the theory of p-adic unit ball. So actually the two-adic unit ball, P is equal to 2Ks. So it is rather a singular surface in two-adic, over the two-adic field. And then somehow there is some general theory. You can lift this two-adic p-adic construction to a over a complex number field. So it is rather abstract existence theorem. And then these guys, Cartwright and Montero, Steger, Japa, they are group theorists. They are trying to compute. They try to find a suitable subgroup of PU21, which could result in a fundamental group of Mumford. So so kind of fake project plan. So they found a couple of groups. And then Ishida and Kato proved the existence of two more using their result. And furthermore, Ishida proved that, so it's the Ishida surface. And there is a certain surface which is quotient by a simple group order 168. It's a simple this is ramified. And there's Mumford surface. And this is quotient by the dihedral group of order 8. And this is 21 degree 21 map. So this is unramified. Galois, and this is ramified, not Galois.
Does Mumford mean the left of Mumford's characteristic?
This is Mumford surface, yes. Yes. Over C, yeah. Here, not Galois means, in topological terminology, this is irregular cover. No, I'm sorry. In topological covering is always unramified. So here, not Galois means it is not group quotient. Yeah. It's not normal, yes. The fundamental group is not normal inside. So here, Ishida surface is an elliptic surface. He did quite a complicated analysis in possible quotient, so that he figured out the structure of this quotient, or V by this group. So this is M27. And then he figured out that the structure, it must be elliptic surface with two multiple fiber, multiplicity 2 and 3. This is simply connected. It's called a one Dolgachov surface. It's a simply connected surface with two multiple fibers of coprime multiplicity. And then I gave another construction of a fake project plane by taking a degree 3 cover and then degree 7 cover. So my construction goes this way. I took degree 3 cover and then another degree 7 cover. So this is my surface. So eventually, my surface is a degree 21 cover, which is Galois. So the group is the unique non-abelian group. Of order 21. So Mumford surface is non-Galois cover of Ishida surface, and my surface is Galois cover of Ishida surface. So yeah, by taking a degree 3 cover and then degree 7 cover of a suitable contraction of 2-3 elliptic surface described by Ishida, which is covered by Mumford fake project plane. And my surface and Mumford surface both are degree 21 covers of Ishida surface. One is Galois, the other is not Galois. Ishida surface is Ball quotient because this is a Ball quotient. So this is actually a Ball quotient by certain group. It turns out that this is a maximal arithmetic subgroup of PU21. And it is not known how to construct it geometrically. So in other words, we don't know yet the, say, defining equation of this surface. We don't know how to construct this Ishida surface. Well, starting with rational elliptic surface, you can make two specific fiber multiple fibers of multiplicity 2 and 3, but the question is there must be certain section, multi-section, which is rational curve. So the existence of such a rational curve is the main problem how to in construction of this Ishida surface in projective geometric point of view. So it is a tensor of a rational elliptic surface. I mean. It's Jacobian, the Jacobian of this surface. The Jacobian of this surface is a rational elliptic surface. It is a principal homogeneous space. It has a negative 3 curve. Here, this negative 3 curve means it is a rational curve, or topologically isomorphic to S2, the sphere, which has self-intersection negative 3. That is a 6th section, meets general fiber 6 times. And then Prasad-Young's classification came in. Their first paper appeared in 2007 in Invenzione, and their addendum appeared last year, 2010. So their classification was motivated or initiated by Klingler's work. Every discrete torsion-free co-compact subgroup having minimal Betti numbers is arithmetic. Here, arithmetic means It's kind of the quite complicated definition, but it is related with the commensurability to a algebraic group defined over number field. So not just arbitrary subgroup of PU21. So here, so that here arithmetic theory of algebraic groups enter here. So it turns out that according to their description, the description of algebraic groups, G bar, in which capital pi is candidate for fundamental group of fake projective plane, in which pi is arithmetic. There is a pair of number field, K and L, and K is totally real. So for example, Q, or Q extended by certain quadratic irrational number, the real number. K is totally real, a subfield of real field, and L a totally complex quadratic extension of K. And there is a central simple algebra D of degree 3 with the center L and an involution iota of the second kind on D such that the fixed point, the fixed element set, fixed subfield of L is equal to K. Here you can think of this, the center L, you can think of this simple algebra D is a 3 by 3 matrix with entries in L. And center L, you can think of center L as a scalar matrix. So this is real 3 by 3 matrix. And this second kind, the involution of the second kind is kind of extension of complex conjugation. So the algebraic group, the K rational point of the algebraic group, G bar K, K rational point of algebraic group is the set of all Z in D such that iota Z is equal to 1. So in other words, Z is kind of Hermitian and marked out by these elements. So there is one Archimedean place, a nu 0 of K, so that the K nu 0, the local field, the algebraic group, the K nu 0 points of this algebraic group is isomorphic to PU21. And G bar K nu is compact for all other Archimedean places. So we see this fundamental group as a subgroup of this. So, and the data, and then this data is rather short, rather long in some sense. And the data determines K, L, and D nu 0 determines the algebraic group G bar up to K isomorphism. And then using Prasad himself, his volume formula, Prasad and Young eliminated most data, K, L, D, nu 0, and making a short list of possibilities where fundamental groups might occur, and which yield a short list of maximal arithmetic subgroups gamma bar, which might contain a possible fundamental group. So in their combined paper, original paper and addendum, Prasad Young exhibited 25 maximal arithmetic subgroups gamma bar that actually contains at least one pi. It turns out that the index of such a pi in gamma bar is 1, 3, 9, and 21, and that the index depends only on gamma bar. And all pi's in the same gamma bar have the same index. So it's a corollary. This corollary of these four authors. The automorphism group of any Faker project plane must be isomorphic to the normalizer fundamental group mod fundamental group, where normalizer is the normalizer fundamental group inside the maximal, inside a maximal arithmetic subgroup gamma bar, or PU21. So in particular, the fundamental automorphism group is one of these four. So the index 3 case, then automorphism could be trivial or C3. Index 9 case, trivial or C3 or C3 square. Index 21 case, then trivial or C3 or 7.3. So the full automorphism cannot be just 7, cyclic group of order 7. So Cartwright-Steggers computation, they give actual computation. They give the generators of each group. So they use a computer algebra system, a very clever way. So they try it out. I mean, they add one suitable generator, and then they compute the group. And then if the group is not big enough, and then they add another generator, and so on. So there are exactly 25 gamma bars of the conjugacy. And there are exactly 28 classes. There are 3 fundamental groups, each belonging to 2 non-conjugate gamma bars. So in this case, they call a class. Here, class means 2 fundamental groups belong to the same maximal arithmetic subgroup gamma bar, then their corresponding Faker project planes belong to the same class. So Mumford surface and my surface belong to the same class. So here, Mumford surface must be someone like, and my surface something. Here and pi 1, both a subgroup of gamma bar. This is one case. And there are, so it turns out that there are exactly 50 fundamental groups. And Kharlamov and Kulikov proved that no Faker project plane can be anti-holomorphic to itself. So if you change the structure by complex conjugation, then the surface is not isomorphic to the original one. So for this Faker project plane case, so each pi corresponds to 2 Faker project planes, complex conjugate to each other. So there are exactly 100 Faker project planes. So the number is rather too good to believe.
You say the Faker project is not homomorphic, or you don't know Faker project is homomorphic or not?
No, they have different fundamental groups. Yeah. So up to homomorphism, there are 50 Faker project planes, because complex conjugate, these pairs are homomorphic to each other. They are also diffeomorphic to each other, but complex structure are different. So up to complex, as a complex surfaces, there are exactly 100 Faker project planes, but there are exactly 50 topological types. They're all different fundamental groups. And about 34 or 50 have non-trivial automorphism group. So this is enough reason to study the possible quotients of Faker project plane. Here's the, as I said, my surface, Keum surface, and Mumford surface both are degree 21 curvature of Ishida surface. One is Galois, the other is not. And they belong to the same class. And this class consists of 4 Faker project planes, I mean 4 possible fundamental groups. So more precisely, this class consists of 8 Faker project planes. So quotient of Faker project planes. Quotient of Faker project planes, we classified all possible structures of the quotient surface X mod G and its minimal resolution. Here's the result. Here X is a Faker project plane, and G is a arbitrary automorphism group. So G could be cyclic group order 3 or order 7, or 3 elementary group order 9, or non-abelian group of order 21. So if G, say, G is cyclic group order 3, then X mod G is a Q homology projective plane with 3 singular points of type 1, 3, 1, 2. Here, today's talk, Namun Lee already explained the notion of quotient singularities. This case, the 3-dimensional case, this is the singularity mod. Here, like this. Matrix notation. So in the matrix notation, yeah, it is like here zeta is the nth root of unity. So it has an isolated singularity at the origin. So that the singularity
G is also subgroup P to what?
what is G?
G.
No. G is a kind of G tilde modulo fundamental group. So G tilde is a subgroup of certain some gamma bar. Okay? It's P2 projective unitary group. Yeah, here this must be normal here. So in this case, the quotient always has only 3 singular points. So the first case, if G is a cyclic group order 3, then the quotient is a Q homology project plane. This means that it has same rational homology with CP2. So it is a singular surface, but it has a first Betti number 0 and second Betti number 1. With 3 singular point of type 1, 3, 1, 2, 1 over 3, 1, 2. And the minimal resolution is minimal surface of general type with PG0 and K square equals 3. Here, the minimal surface of general type with this invariant PG0 vanishing genus and K square equals 3, it has moduli space. So it has virtual moduli has dimension 6. So it has, but this one X mod G has a certain mild singularities. So these surfaces appear as a kind of a deformation of a smooth minimal surface of general type with PG0 and K square equals 3. So this is the reason why it could be easier to find such X mod G, such a surface. And so this is the reason why I study the possible quotient. And if the group G is order 9 and 3 elementary, then X mod G is a Q homology project plane with 4 singular points with same type, 1 over 3, 1, 2. And its minimal resolution is a minimal surface of general type. This time K square is equal to 1. And if G is order 7, then the quotient is a Q homology project plane with 3 singular point of type 1 over 7, 1, 5. So these singular points its minimal resolution correspond to a chain of minus 2 curves. This corresponds to this quite well-known standard theory of algebraic surface singularities. And its minimal resolution is 2,3 or 2,4 or 3,3 elliptic surface. And if the group G is about 21, then again it has 3 of type 1/312 and 1 of type 1/715. And its minimal resolution is again 2,3, 2,4 or 3,3 elliptic surface. So these are Godara dimension 1 elliptic surfaces. And in this case, it is simply connected. In this case, well, this kind of elliptic surfaces is quite well known. The fundamental groups can be easily read off from the multiplicities. This is result of Dolgachov based on Van-Kampen theorem. So this is relative prime, so it's simply connected. And the fundamental group is Z mod 2. In this case, fundamental group is Z mod 3. So the fundamental group is a cyclic group of order which is greatest common divisor of these two multiplicities. So the result was, this result was obtained by general consideration, not using the Ball quotient structure. Here a Q-homology plane, Q-homology projective plane is a normal projective surface with the same Betti numbers as CP2. Here maybe in most cases I assume it has only quotient singularities. A FPP, fake projective plane, is a non-singular Q-homology projective plane. Hence, every quotient of a fake projective plane is again a Q-homology projective plane, because the first Betti number 0, so its quotient must have first Betti number 0. And first Betti number 1, and it's algebraic, so its quotient has always second Betti number 1, then algebraic, so its quotient is also such a surface. And an AB elliptic surface is a relatively minimal elliptic surface over P1 with Euler characteristic 12, having two multiple fibers, multiplicity A and B respectively, as I explained before. It has Godara dimension 1 if and only if A bigger than or equal to 2, B also bigger than or equal to 2, and their sum is bigger than or equal to 5. It is an Enrique surface if and only if A equal B equal 2, and it is rational if and only if A equal 1 or B equal 1. All AB elliptic surfaces have PG and Q are both 0. Here PG, by definition, is a dimension H2. Q is classical notation is irregularity. So if X is smooth, then this is nothing but the dimension of the global holomorphic 2 forms, and this is global holomorphic 1 form. But if it's not, X is not smooth, but still we use this notion. If X has only quotient singularities, these are modern terminologies, log terminal singularities, then PG of X is equal to PG of its minimal resolution. So it doesn't change. Irregularities also stays the same because these are rational singularities. So we can use and then it is natural question. So whether it's possible to construct fake projective plane from one of such, such quotient. Given a Q homology projective plane satisfying one of the descriptions 1 through 4, 1 through 4 is this. So any, for example, any Q homology plane with 3 singular points of type 1/3, 1, 2, and its minimal resolution is minimal surface of general type with PG0 and K equals 3, say. And then can one construct a fake project plane by taking a shootable cover or composition of 2 shootable covers? In other words, do these descriptions characterize the quotient of fake project planes? So the answer is yes. So suppose, here's my theorem. Let Z be a Q homology project plane satisfying one of the descriptions 1 through 4 above. Then a fake project plane can be constructed from Z. It's the outline of the proof. By a lattice theory, the basket of singularities, the information of singularities, implies the existence of a shootable cover branched exactly at those singular points. So remember, so this quotient, it's suppose it is a quotient by some other fake project plane, then it must be isolated. The automorphism must have isolated fixed points. So here, the basket implies the existence of shootable cover or composition of 2 shootable covers branched at the singularities and yielding a non-singular surface X. The case, say that this is the first case, Z has 3 singular points of type 1, 3, 1/3, 1, 2. The cohomology lattice is unimodular of signature 1, 6. This is the cohomology lattice. So usually, in general, this one contains some torsion. So if you model out torsion, then this is the lattice, free Z module, with intersection form, which is unimodular by Poincare duality. And one can show that there is a divisor L such that it's 3 times L, the divisor notion, or just line bundle notion, and then the L tensor 3 is equal to certain divisor B supported on the exceptional locus of the resolution and the torsion divisor. This is purely a lattice theoretic argument. So if pi has order not divisible by 3, then the modified L okay. If pi has order not divisible by 3, then a modified L, so you can get rid of this tau somehow by multiplying the order of tau somehow, and then you can take another L and another B, so that you can assume that the tau equals 0. Then a modified L gives a C3 cover. If you have so here's the surface, our surface Z. Here's our surface minimal resolution here, and then here's a kind of B. So B lies on. So B lies on a singular point of Z here. And then the degree 3 curve actually lives in here. This is this is a certain line bundle L corresponding to this divisor L. And then say V, say W. So the line bundle, if you view this line bundle as a total space over Z tilde, and then by this, so here we assume 3L equal B, So locally, so you can think of the defining equation of B, and then the Z is the coordinate. Is probably not good notion, maybe T. T is the coordinate of L. So you can think of this triple cover branch that B. So the W is defined by this. So W is locally. And then somehow you can blow down so that you can get something X here. This is FPP, turns out. So, and this cover, so this cover branch only along B. So this cover branch only along the singular points. And then, and also the singular points is of type 1, 3, 1, 2. So this only way of degree 3 cover, so that, so the point lying over the singular point is a smooth point upstairs. So this is the reason why I got smooth surface upstairs. So, and then it is easy to see this is kind of a Hurwitz type of argument. Euler number, you can compute Euler number of X and canonical class, and Kx is an F. So PG equal Q, we get. So K2 equal 9 and C2 is equal 3. So this surface X is again on the line satisfying the Miyaoka-Yau inequality, the equality of the Miyaoka-Yau inequality. So it must be a Ball quotient. So and also it has the geometric genus and irregularity must be equal to each other. So it remains to show that they both vanish. So it's a fact. A surface of general type with K square equals 3 times C2 is equal 9 has at most, has PG equal Q at most to 2. So I'll get back to this fact in a few minutes later. And then finally show that the case 1 or 2, PG equal Q equal 1 or 2, do not give such a quotient yet. So here I use the Albanese map. So consider the Albanese map. This sort of, here in this case, 1 or 2, then you have holomorphic worm forms. So you can think of this worm form, you can think of the integral of these worm forms over a curve. So you fix one point, and then if you're given any point, and then you can think of the arc or path connecting this point, fixed point to this given point, and then you can think of the integral. So this map is given by this integral.
Are there any known example with the K equal to 9, C equals 3, but positive P genus?
Yes.
Examples?
Yes. Yeah. That I go. Yeah. Yeah. There is only one example. Actually, that was given by Cartwright and Steger. Yeah. So people believe that these surfaces doesn't exist. So it should be PG0 or Q equal 0. But the two case, PG equal Q equal 2 case, we don't know the existence. But one, now we have one example. And then, and also the holomorphic Lefschetz fixed point theorem. This is a special case of Atiyah-Singer index theorem for elliptic operators. And also easy topological Lefschetz fixed point theorem to an automorphism of the 3 or the 7. Then we can get rid of these two cases. So this is a remark on the surfaces with K square equal 3 times C2 equal 9. A surface of general type with such invariant has PG equal Q at most 2. It's a proof. A surface of general type with C2 equal 3 cannot have a fibration of a curved genus bigger than equal to 2. This is general type, so that each general fiber must have genus at least 2. So if the base curve is at least 2, then the product of two Euler number is already 4. So if you have a singular fiber, then the Euler number will increase. So there is no such fibration. So by Castelnuovo-de-Frankis theorem, PG, we have this inequality. PG is bigger than or equal to 2Q minus 3. So in our case, PG equal to Q. So we have this. And the surfaces with PG equal Q equal 3, your question was PG equal 0, yeah? Positive, no, yes, okay. Of course, yeah, there are many, yeah, there are some other examples, of course, here. Here's PG equal Q equal 3 were classified by Catanese and Siliberto, Mendes-Lopez, and Hecon and Paradini. Such a surface cannot have this. So this one doesn't relate to your question. And a surface of general type with k square equal 9 and C2 equal 3 is a Ball quotient. And the existence of surfaces with PG equal Q equal 2 is not known. But Cartwright and Steger have also computed all arithmetic quotients, not only the fake projective planes. He computed all possible quotient by a certain arithmetic subgroup. They found one arithmetic quotient with PG equal Q equal 1. So people believe this should be the only one other than fake projective planes, but still it's not known. The difference is this. So some such surfaces may not be arithmetic quotient of Ball. So they are Ball quotient, but they may not be arithmetic. So under the condition that being arithmetic, there are only fake projective planes and this surface. Okay, so time is up. So let me. Okay. So let me stop here. So.